Welcome to this explainer. Today, we're diving straight into a mathematical mystery that literally unlocks the hidden secrets of square numbers. If you've ever thought number patterns were just random rules you had to memorize, well, prepare to see them in a completely new light. We're going to treat today's topic as a step-by-step lesson, decoding the underlying logic of math that makes everything click into place. Here is our step-by-step roadmap for today's lesson. We'll start with the 100 locker puzzle, move into unlocking factor pairs, define exactly what a square is, learn how to spot perfect squares, and finally, look at summing up odd numbers. Let's start right off with section 1, the 100 locker puzzle. So picture this. The incredibly clever Queen Ratnamanjari wanted to leave her massive fortune of precious stones to her son Khoisnam, but she really didn't want the rest of the extended family pestering him about it. So she comes up with a brilliant test. The royal minister brings Khoisnam and his 99 relatives into the secret room, right? And inside there are 100 closed lockers. The queen's will states that whoever figures out which lockers are left open at the very end of a highly specific process gets the whole shebang. Now, the rules here are super exact, and honestly, this is where our math lesson really kicks off. Each of the 100 people takes a turn. Person number 1 goes first and touches every single locker, opening them all up. Then person 2 comes along and toggles every second locker, the second, fourth, sixth, and so on. By toggling, I mean if the locker is open, they close it, and if it's closed, they open it. Then person 3 toggles every third locker, person 4 toggles every fourth, and you guessed it, this exact pattern just keeps going all the way up to person 100. So here's the million-dollar question. Which of those 100 lockers will actually remain open at the very end? Well, our guy Khoisnam figured it out instantly, entirely in his head, before anyone even moved a muscle. How is that possible? He realized something absolutely crucial. To know a locker's final state, you don't need to act it all out manually. You just need to know exactly how many times it gets touched. Which brings us nicely to section 2, unlocking factor pairs. Think about it like this. Every single time a locker gets toggled, it's actually being acted upon by one of its mathematical factors. Take locker number 10, for example. It's going to be touched by person 1, person 2, person 5, and person 10. And hey, those are the exact factors of 10. The trick here is, if a locker is touched an even number of times, it's going to end up closed. But if it's touched an odd number of times, it stays open. Let's put that into perspective by comparing locker 6 and locker 36. So locker 6 has the factors 1, 2, 3, and 6. They naturally come in pairs, right? 1 times 6 and 2 times 3. That's 4 factors total. Since 4 is an even number, locker 6 gets toggled an even number of times and slams shut. But look at locker 36. It has the pairs 1 and 36, 2 and 18, 3 and 12, 4 and 9, and then boom, it has 6 times 6. Because the factor 6 partners with itself, it's only counted once as a person touching the locker. This gives 36 a total of exactly 9 factors, and since 9 is an odd number, locker 36 stays wide open. And that leads us right into section 3. What is a square? That cool little anomaly we just saw, a number partnering with itself, is the core of our whole lesson today. So, what is a perfect square formally? It's simply a number multiplied by itself. 1 times 1, 2 times 2, 6 times 6. In general terms, for any number n times n equals n squared. Because they have that one unique factor that multiplies by itself, perfect squares are literally the only numbers out there that possess an odd number of total factors. And just like that, the puzzle's answer is hiding right in plain sight. Only the lockers representing perfect square numbers will stay open to reveal the treasure. Khoisnam knew that lockers 1, 4, 9, 16, 25, 36, 49, 64, 81, and 100 were the only winners here. He didn't have to lay a finger on a single locker, he just had to know his perfect squares. Pretty brilliant, right? All right, let's keep building on this. Section 4, spotting perfect squares. As students of mathematics, we're always looking for good shortcuts to verify our work. If you list out the squares of the first 20 or 30 natural numbers, a massive pattern pops up right in their final digit. Perfect squares always end in 0, 1, 4, 5, 6, or 9. So you can confidently rule out a ton of numbers just by taking a quick glance at their last digit. If you see a number ending in a 2, 3, 7, or 8, you know instantly with absolute certainty there is no way it's a perfect square. Okay, but a quick word of caution before you go wild with this trick. While a perfect square can end in a 6, like 16 or 36, that doesn't mean every single number ending in 6 is a square. Just look at 26. It ends in 6, sure, but there's no whole number you can multiply by itself to actually get 26. So while looking at the last digit is an awesome tool for proving a number is not a square, if it does end in an acceptable digit, you've still got to do the math to confirm. And checking for zeros is another great shortcut. 10 squared is 100. 20 squared is 400. 100 squared is 10,000. Are you seeing the pattern here? For a number ending in zeros to even be considered a perfect square, it absolutely must have an even number of zeros at the end. A number with 3 zeros, like 1,000, it simply cannot be a perfect square. No way. Moving on to our final stop, Section 5, Summing up odd numbers. To really deepen our understanding today, we need to look at this beautiful, almost magical connection between squares and odd numbers. Let's look at the gaps between consecutive square numbers. The jump from 1 to 4 is 3. From 4 to 9 is 5. From 9 to 16 is 7. If we flip this around, a stunning pattern emerges. If you add up consecutive odd numbers starting from 1, they perfectly build the sequence of square numbers step by step. 1 is 1 squared. 1 plus 3 is 4, which is 2 squared. 1 plus 3 plus 5 is 9, 3 squared. 1 plus 3 plus 5 plus 7 is 16, 4 squared. It works every single time, without fail. And we can use this exact pattern to solve some seriously complex problems with ease. Let's say you already know that 35 squared is 1225. That actually means 1225 is the exact sum of the first 35 odd numbers. So what if you suddenly need to find 36 squared and you really don't want to do the long multiplication? You just add the 36th odd number to 1225. To find any nth odd number, the quick formula is just 2n minus 1. So for the 36th odd number, we do 2 times 36, which is 72, minus 1, giving us 71. Add that 71 right onto 1225, and boom, you get 1296, which just so happens to be exactly 36 squared. These patterns aren't just neat little parlor tricks either. They are powerful visual proofs that give us totally different ways to calculate and verify perfect squares without ever touching a calculator. Actually, you can even use the reverse of our addition trick as a sort of subtraction test. Try this. Take a number, let's say 81. If you repeatedly subtract consecutive odd numbers, -1, -3, -5, and you eventually land on exactly 0, you have mathematically proven it's a perfect square. If you drop below 0 without hitting it, then it's for sure not a square. So we've seen how Queen Ratnamandari's Locker puzzle opened the door to some incredibly elegant rules for perfect squares, factor pairs, and odd number sums. But as we wrap up this lesson, I want to leave you with one final provocative thought. We've mastered multiplying a number by itself once to get a flat 2D square. But what happens if we multiply a number by itself 3 times? What kind of fascinating new patterns, rules, and mind-bending puzzles emerge when we step off the page and into the 3D world of cubes? Well, that's a lesson for another time. Thanks for joining me on this explainer, and remember to keep looking for those hidden patterns.